Hello, I'm Giray Soytürk and I'm here to present you my homework, which is the second homework of the computer vision lesson. So this homework is about camera parameters estimation, and I wrote some code to do that in MATLAB, of course. I'm going to show the code and I'm going to explain what I did uh, with my code and which line of code represents what. Okay, so let's start. Open our MATLAB, and first of all I have to say that I wrote codes into different script files because one of them includes the non-noisy points estimation, camera parameters estimation from non-noisy points. So let's look at that first. We have 268 points given, and we have to match all the points from 3D real world points to 2D image points. How can we do that? Let me explain how we can do that. Camera is a matrix. Actually, camera is a 3x4 matrix, and it satisfies the equation which is 2D image point equal to camera matrix multiplied with 3D real world points. So basically, what camera matrix does is project a real world point to the two-dimensional image plane. So after all that explanation, let's continue to look at the code. We have Q matrix here. Q matrix is going to help us with the estimation of the camera matrix. So points 3D is the matrix which is the real world points are stored in, and points 2D is the matrix which stores the image point values. So these points 3D and points 2D matrices are fed with external data, which are imported from here, import data, and when we first implement it, these values are in table data type, so we have to convert them into arrays in order to make matrix procession. So let's continue. We have a for loop here. This for loop is this for loop runs or loops for every number for the number of points, because for each point we have to find a correspondence. For a real world point, we have the correspondence for it in the image plane. in 2 dimensions. So we are constructing our Q matrices, which are consists of these values. As we can see, we have some multiplication here, and after that we have B matrices. B matrices are storing the 2-dimensional B matrices are storing the not P matrices. Actually, let me explain that in this way. We have one Q matrix and we have one B matrix, but we have to um, find 2 values for each point in Q matrix and in B matrix as well. So we have to write these way. We have to assign values in that way. So B matrix is going to store the 2D points in this way. So now we are at the point of estimating the camera matrix, which is 3 by 4, and we are obtaining it from this equation. This means we are using Q matrix and B matrix, and we are dividing B matrix to the Q matrix because MATLAB has this divide operation. Actually, we are not dividing the matrices because there is no division. There is no division in matrices, but MATLAB does this for us by using inverse of a matrix. So we obtained our A matrix, and the A matrix is we modify our A matrix a bit, and we get these A matrix. In our A matrix, because of its size, we know that there will be 12 elements, 12 values, but one of them, the last element, the last value of the A matrix is 1, and the other ones, the other 11 parameters, the other 11 values are not 1, because they are going to help us. They are making the multiplication satisfied with 2D points equal to camera matrix multiplied with 3D real world points. So we are from the beginning I am explaining this, and now here we are doing the thing that I'm explaining. 3D points multiplied, actually camera matrix multiplied with 3D points equals to 2D points. Now we have to do this for loop, because in order to satisfy the dimensions of the matrix, we, as you can see, done some trick here, a small trick, and we now have to divide every element of the of every column with the latest with the last element of this column in order to make this equal to 1, and because when we are representing our 2D image points, we write x, y, and 1. So we are trying to obtain this notation. So after doing that, we are at the edge of something exciting and something important again. We are now estimating the error values. Why we are doing that? Because the error will give us the robustness or the robustness is, I think, the right word to use here, of our model, robustness of our model. So we have the image points given externally, and we found new values using our A matrix. The A matrix is the camera matrix. We found it on here, and we found some 2D image points as well with using this A matrix. Now we are going to compare them. We are going to take the differences and see whether we found them almost the same, because if we did not, then our A matrix is obviously wrong. But we are taking the differences, and of course we are using the x2 minus x1 square plus y2 minus y1 square, and square root all of them. This rule, this formula for estimating the error. So we are doing that here. We are taking the squares and sum these squares and take the square root of these sums. So after that, I want to show you the errors that I found. These are very small values actually, as we can see. We are finding the errors at 1 divided by 100,000, or sometimes it comes 1 divided over 10,000 and 1 divided over million. So this means that we found our A matrix correctly, because these values are nearly zero, and the points are almost the same, almost identical points. Let me show you some of those points. These are the points 2D matrix is this matrix stores the external given points, given image points, and points 2D new is the values that we found with our A matrix, and we can see that they are identical. They are almost identical, because there is a very small error between them. So we are done with the error subject, and now we are now I'm going to talk about camera parameters estimation. What are camera parameters and how we can estimate them? So let's get it on. We are using T1, T2, and T3 vectors, which as you can see, are constructed from the A matrix that we found. We are using the first three columns of every row to determine what the T1, T2, and T3 is, and we got C1 and C3. These are from the pinhole model. Yeah, these are from pinhole model, as we can see them on here. We have to estimate and construct these T1, T2, T3, C1, C2, because we are going to use the pinhole model formulas to determine what camera parameters are. Now I want to talk about the camera parameters, and there are two types of camera parameters. One of them is intrinsic parameters. Intrinsic parameters are modeling the behavior of the internal geometry of the camera, and we are estimating them with these formulas: U0, alpha U, V0, alpha V are the intrinsic parameters, and we are using, as you can see, T1, T2, T3 to estimate them. And we are, of course, dealing with vectors, and when we are using vector multiplication, we have to use dot and cross product. So now it's time to talk about extrinsic parameters. Extrinsic parameters are the second type of camera parameters, and extrinsic parameters models the behavior, not behavior, situation and rotation. Of the camera in the real world. Intrinsic parameters are dealing with the camera's inside. Intrinsic and inside, we can remember it in that way. Intrinsic parameters are dealing with the internal camera geometry, but extrinsic parameters are trying to model the situation of the camera in 3D world coordinate system. So we have 6 extrinsic parameters, and they are R1, R2, R3, Tx, Ty, Tz, and we are finding them. We are estimating them with these formulas, and we are again using T02, T1, T3, and so on. Now we estimated our parameters, intrinsic parameters and extrinsic parameters, and it's time to construct our camera matrix again. And why we do that? We found a camera parameter earlier at the beginning of our code. We found it, but from matrix factorization, we know that camera camera matrix can be factorized into two matrices, and one of them is constructed by intrinsic parameters, and the other one is constructed by extrinsic parameters. And we are constructing our camera matrix again, this time with our intrinsic and extrinsic parameters using this formula. And now we have, again, we are dividing the last elements, each element, we are dividing each element to the last element of the matrix. So as we can see, we have a matrix here, and we have an a parameter. I named it a underscore param because we've constructed it from camera parameters. So as we can see that they are identical same, and this is a good sign because it shows that we did a good job and we find the camera parameters and camera matrix correctly. So this was for the non-noisy points. We didn't use RunSec here, and now I'm going to show you the other script that I wrote, but actually I couldn't get it correctly work, the ransack part. Actually I did something, some things, I wrote some code, I construct some loops, try to understand the concept. I actually understand the concept of ransack, what it does and why we use it. I know that I'm aware of that, and I'm gonna explain it to you, but the code that I wrote does not work quite well, not good. So I'm going to first I'm going to tell you what RunSec is and why we use it, and then I want to show the code that I wrote, and not all of it, but some parts of it may look that may show that I understand the concept of RunSec. So RunSec is short for random sample consensus. What that means? So we have a data set. And we want to model the data set with a line. So when we are, I mean, of course, we are not restricted with line, but I'm just making a point here. We are trying to model a data set, and we are trying to use lines. We are trying to use the best. We are trying to find the best line to model the data set. So we are in RunSec. We are taking 2 points in the data set and trying to fit a line to them and see how many points are on the line, or how many points are close enough to the point that we can take them as acceptable. In here there's a term inlier point comes in, and what inlier is, when we are drawing our line, we are selecting a threshold. This threshold is this threshold will be our checking key. So if there is a point close to the line that we draw, less than the threshold, we are going to take the point acceptable and we are going to count it as an inlier. So what Ransack does, what Ransack tries to do is to find the best line, and the best line is with the line with the most inlier, the most inlier points. So of course there are some parameters in here. I mentioned them. There is the threshold value. If the threshold value is too big, our model will not be good enough to model our data set, because we are going to accept some non-relatable or non-good points to our model as inliers, because if the threshold goes big, there will be some non-relatable points taken as inliers, and this will destroy our model. But if we took the threshold so small, then maybe not with all data sets, but with some data sets, we can see that there will be no inlier points. Maybe we took the threshold value as 0.00001 and we run the program and we see that there is no inliers. So we are trying to find the best model. We are not trying to find all the points inliers or none of the points are inliers. So this is a important point. Another important point is the repetition number. Repetition number is in Ransack we are randomly selecting points and drawing lines, passing through them, and we have to do this process again and again and again and again. But for a large data set, if we do this for 100 times or 1,000 times, it may not be trustful, it may not be good, because maybe there are billions of possibilities, permutations that we can try. But if we strict it with its very less amount compared to the permutation probable permutation number, our model, our Ransack algorithm will not be a good game. So I told you that I wrote some code, and I again told you that it does not work very well, and I know it has some errors, but I tried to show you that I understand Ransack and what it does and why we use it, and how it will affect or the changes of the parameters of the ransack, I mean the threshold value and the repetition number, are the top of the importance list. So I tried to make conclusions, thinking with parameters and with their changes, of course. So this is it. Thank you for listening me. Thank you for uh, giving me this time of your life, uh, from your life. So I hope you enjoyed it, and thank you again.